Yeah, so moving forward with our next presentation titled Polyurethane Flexible Joint as an Adhesive Bonding, the Safety Tape Solution. And I would like to introduce the speaker for this presentation is Dr. Arkadiusz Kwiecień. He is a full professor at Cracow University of Technology, where he has worked since 1995. He is known for developing innovative methods for structural repair using polymer flexible joints. In 2016, he founded Flex and Robust System, a spin-off company focused on polyurethane flexible joints and fiber-reinforced polyurethanes, FRPU, with over 260 scientific publications and leadership in multiple international research projects. Professor Kwiecień work has had significant impact, particularly in the seismic engineering. He is also active in global organizations such as RILAM and so. So let's welcome him and listen to his presentation.
So thank you very much for introduction me. Good afternoon to everybody in USA. If somebody is from Europe, so also there is. So thank you for introduction of me. I would like to present today, after short introduction, bonding problems in strengthening of deteriorated structures and relevant solution for it. I mean flexible polyurethane adhesives. Also, I will compare stiff epoxy adhesive versus flexible polyurethane adhesives. And I will talk about possibility of additional safety and monitoring ability in post-failure mode. Also, I will present some possibility of strengthening of not damaged concrete structures using stiff epoxy and flexible polyurethane adhesives. And also I will talk a few words about the properties of polyurethane flexible adhesives in the aspect of hydrothermal properties, and also I will give some words about the ongoing project Horizon 2020 about some kind of certification of innovative solutions, and then in summary I will present most important features of polyurethane flexible composites. If we go around the world, of course, we have many catastrophic events like earthquakes or other one that can influence the damages of the structures. So if the damages are so serious that are presented, especially according to infrastructure like bridges or viaducts, in this case, we have problems with escape roads. So it should be avoided to allow for such catastrophic events according to infrastructure. Of course, if they are damaged or they are seriously corroded, we have three options. One, we can demolish and reconstruct them, or we can do nothing, but the most appropriate is retrofitting. It, of course, requires less time and less money, and it has lower environmental impact. Nowadays, we use for that carbon fibers as the composite material that is able to improve the structural properties that was presented in the last presentation. So I would like to show shortly effectiveness of such intervention, because this is the view of three buildings that were constructed in Turkey, in Hatay. In 2008, one of these buildings was strengthened with composite fibers by Professor Alper İlki from Istanbul Technical University. And 15 years later, during the very huge earthquake in Turkey, in Hatay, two buildings were collapsed, but the building that was strengthened with carbon fibers survived this very catastrophic event. So it is some kind of proof that it is suitable and it is worth to use composite materials for strengthening of structures. Coming to the problems that we have with our infrastructure, we know that with many years, the structure starts to deteriorate, first by initiation of corrosion, then by formation of cracks. The life cycle of reinforced concrete structures is shortening, and in this case, we have to take into consideration possibility of turning off this kind of structures and to stop exploitation of that. So to have a possibility to explore it more, we should think about some improvement. Of course, if the structure is seriously corroded, it can cause the damages, sudden damages like it is presented in viaduct in Fossano in 2017, where very corroded concrete was the source of this catastrophic event. Of course, if we would like to improve the strength nowadays, the most popular is using of composite strengthening, mainly carbon fiber laminates is very popular, but there is the requirement of using it. As FIB bulletin presented in 2001, the minimum requirements for the strength concrete is at least 1.5 megapascal in of tensile strength of the concrete measured in pull-off tests. So if the structure is very corroded and concrete is of poor quality, typically has lowest values. And the question is if there is any solution for such problem, if we would like to use composite materials. One of the most critical source of damages is stress concentration. When we use brittle materials, we use high stiffness materials. In this case, we have a stress concentration problem, especially if the materials are of high stiffness. This appear mainly in the places of cracked structures, but also in the bonding area where the composite material, high stiffness composite materials, is bonded to the very weak substrate. In this case, stress concentration causes micro cracks, then mine crack, and the structure goes to failure. So how to solve and to manage with this problem? It is very simple, because to avoid stress concentration, we should evenly stress redistribute. So in this case, we are able to protect the weak substrate because evenly redistribute stress is, of course, of lower intensity. So if we bond two stiff and high strength materials or weak materials, if we do it with brittle and stiff materials like epoxy resin, we can expect stress concentration. If we apply more flexible material, in this case, we redistribute the stress more evenly, and we can make more effective bonding of such application. So nowadays, we use typically the polymeric resin, mainly epoxy, in fiber and steel reinforced polymers. Also, in the last 20 years, we use mineral cement or lime mortar as a matrix in strengthening of structures. In this case, we use fabric reinforced cementitious matrix, FRCM, textile reinforced mortar, TRM, or steel reinforced grout, SRG. Also, now it is available to use highly deformable polyurethanes, fiber or steel reinforced polyurethanes, and this kind of solution is suitable for strengthening of materials, mainly concrete or also masonry, when the tensile strength of this substrate is very low, I mean under 1.5 megapascal. Let me do assumption for the next comparison presentation that brick and weak concrete is practically of the same strength. So in pull-off test, we have under 1.5 megapascal. So I would like to present some tests. This is the brick tested in 4-point bending. So original brick was broken. Next, in the place of crack, the brick was strengthened, rebonded again with 3 kinds of materials. If we assume that 100%, this red bar, is the original strength of the brick, and we repair it with cementitious mortar, strong cementitious mortar, we are able to receive lower ultimate strength. When we apply epoxy resin, high strength epoxy resin, in this case, we are able to improve about 7% the strength of the weak material. When we apply flexible polyurethane, in this case of PM type, you can see that the increase of ultimate strength is almost double, and also the damage is in form of cohesive failure of polyurethane. Why it is? Because if we have brittle material and high strength, we have a lot of stress concentrations between gravels, and they can form micro cracks and then link in main crack. When we rebond it with stiff material, we do not improve the situation. But if we do it with flexible material, in this case, we redistribute the stress more evenly, so we are able to increase the ultimate strength. If we consider shear lap test, singular shear test, so in this case, you can see that if we bond the composite material to the weak substrate, but with stiff epoxy resin, in this case, we have stress concentration that after initiation the crack propagate through the whole bonding area. If we bond the structure with flexible material, in this case, we redistribute the stress more evenly, so we reduce this peak of stress concentration, we can protect the weak substrate, and also increase the ultimate force. So this is the example, 2 cases, CFRP material and SRP material, so carbon and steel fibers as strengthening material, with epoxy resin, this yellow bar, and blue one is presented with flexible polyurethane. So you can clearly see when we use epoxy resin, the ultimate load, the capacity is up to 7 kilonewtons. If we apply it in the same system, the polyurethane, flexible polyurethane, we received 12 kilonewton of ultimate system. So you can clearly see both this system, one with steel fibers, another one with carbon fibers. But what is very tricky, when we did directly the same test on the same brick, the same system, the same setup, but instead of epoxy resin that we had 7 kilonewtons for carbon fiber, when we used the polyurethane flexible adhesive, we received 12 kilonewtons. But when we replaced with flexible polyurethane the carbon fiber with grass, I mean bamboo fiber, so we directly received the same ultimate load value. So this is simple proof that the key point in bonding is the adhesive, not strong carbon fiber or strong other composite material. So also when we compare steel reinforced polyurethanes, I mean that in this case we have steel fiber bonded with polyurethane flexible matrix, and we compare it with stiff adhesives, so you can see clearly the behavior of this system. If we increase stiffness of the polyurethanes, we receive higher value, but of the same stiffness. But when we apply flexible polyurethanes, in this case, we receive much higher ultimate load than in the case of stiff epoxy resin, and also very high damage energy. This is the area under this curve. What is also tricky, if we use some composite materials in buildings, masonry buildings, in this case we have plasters. So we did some such kind of comparison tests. Mainly, we bonded the steel fibers directly to the bricks. So this is this blue line. When we bonded the same system, but by interface, I mean cementitious layer, so we received this kind of behavior. If we used very weak lime mortar, because this kind of material is used in heritage structures in Europe, so in this case, we receive directly this red line. So you can clearly see that the behavior of this system, all this system, is very similar to behavior of this flexible bonding material. If we compare in literature in the same scale the effectiveness of this system bonded on the plaster with flexible bonding, you clearly see that it is more effective than lime mortar strengthening with composite materials, the same steel fibers as a matrix. Also, when we use geopolymer or polyurethane epoxy resin, polymer epoxy resin, in this case, all these systems are weaker than in the case of steel reinforced polyurethanes when we use flexible polyurethane matrix. I also present the ability of this kind of matrix to deform and transfer and dissipate energy when the load is dynamic or it is in fatigue. So we used it in strengthening of weak masonry infill when we had the reinforced concrete frame system. In this case, we used glass fibers in polyurethane matrix that were bonded to reinforced concrete columns and slab, and also to the masonry. So these both systems were constructed on the 3D real scale building that was put on the shaking table, and we were able to protect this structure against out of plane and also in plane failure. So I would like now to present you some cases and movies from this shaking table. Mainly on the left hand side, you can see the masonry infill wall. It is protected here in other type of flexible bonding, but let me show you how it works. So you can clearly see that the structure is losing their stiffness, and finally at the end of this test it was not collapsed due to protection with polyurethane flexible bonding and the interface between masonry and reinforced concrete structure, but the global stiffness were lost from 100% up to only 6%. After that, we protected this kind of infill walls with RPU system. So in the middle, you see protection against failure of this kind of wall without any special application, smoothing or the surface. We bonded directly the fibers using the polyurethanes, and in this case, we were able to stiffen the whole structure. The owner of the shaking table was unable with this system to damage this kind of structure, so they promised to damage it with force vibration in resonance, mainly by application on the top special exciters, and try to damage it also. As you can see, in resonance, the test during 2 hours, when the duration of this test was 2 hours, they were unable to damage this structure. Also, the proof of the efficiency of such systems of flexible bonding was as the quick emergency protection of concrete retaining wall that was demolished on the active slope. So in 1 minute, the movement of this wall was about few centimeters. So it was a really serious damage because the house was able to collapse. So we had to stop it. In few hours, we stopped the movement of this retaining wall on active slope. So why this kind of solution is so effective? Typically, if we calculate the composite materials strengthening the brittle materials, we use fracture energy approach. So in this case, we assume that the composite material is stiffly connected with the substrate, and we calculate the energy, the fracture energy that allow us transfer these forces. So if we are with the bonding length, I mean the length of the composite material that is connected to the substrate. If the bonding length is under the effective bonding length, so the ultimate length that is working, so we are with curve in this position. So if we increase the bonding length, we are able to obtain this maximum capacity. And if we obtain with brittle materials and stiff materials this maximum capacity, the peak of stress concentration is cracking the substrate and is transferring up to the end of the structure. So you can see, you can observe this process here. This is mainly with stiff epoxy resin when we use it for bonding of composite material. What is very tricky, when we use the flexible polyurethane adhesives, in this case, we are still under the effective bonding length. So we have the still possibility to increase the capacity of the system. So please see on this on this picture the failure modes, how it is. If we have stiff epoxy resin, in this case we have very sudden failure. If we do strengthening with carbon fibers but using flexible polyurethanes, you can clearly see that this system is some kind of safety tape, because we can see the warning, so we can see deflection. Also, we can hear some voices when concrete is cracking, but the structure, of course, we fail finally when we use not so flexible material. If we use the very flexible material, you can clearly see that the deflection is very warning. So in this case, people can escape from such structure, or emergency also teams can rescue people. But what is very interesting, and after unloading, the structure moved back to the previous position. So in this case, we give time for evacuation, and also we give time authorities for to make decision how to manage with such structure. Also, as you can see here, there is high stress concentration acting on the composite material, where typically, if it is stiff material, such structure doesn't work, but with flexible material, it is able to work. If we compare the effort of this composite material when we have stiff epoxy resin, we can compare it here according to the load. Yeah, but finally, we can expect very sudden failure, especially in the weakest part, that is reinforced concrete, place of location of reinforcement in the concrete. If we compare the same system but with flexible adhesive, in this case, you can clearly see that the effort is higher. Also, as you can see on this movie, the system is hanged on the composite material, even if the structure is very seriously damaged, and is able to transfer load and also to warn people and allow people to escape. Even after the removing this part, you can clearly see that this kind of flexible material is able to dissipate energy and clearly show how protect against stress concentration the composite material. So composite material is not damaged. So if we would like to protect the composite material because of cracks in stiff epoxy resin, the crack generate in this place very high stress concentration that is acting on the composite material. If we have flexible material, you clearly see here that the crack is stopped in the flexible adhesive layer, and in this case we do not have the stress concentration attack on the composite material, because in this case the stress is redistributed more evenly on the whole surface. So let me say something about additional safety. This is an experiment on the beam that was fired by fatigue tests. So after this fatigue test, lower tensile reinforcement was broken. So after reconstruction, the strengthening and tensile forces were carried out by 3 carbon fibers. 2 of them were bonded on epoxy resin, stiff epoxy resin, and 1 on very flexible polyurethane. So during the test, you can clearly see that in one moment, laminates bonded on epoxy resin suddenly fired and detached, and everything was hanging on this laminate bonded on flexible polyurethane. Here you can see cohesive initiation of failure in cohesive layer. So finally, when we detected the failure, you can see cohesive failure in concrete in epoxy resin and cohesive failure in polyurethane in the case of very flexible polyurethane strengthening. So it is clearly visible on this graph. When we design the structure, we have some kind of design point. Yeah, over this design point, we try not to overcome because we have some kind of coefficient of safety. But if we have, for example, earthquake, it doesn't take, it doesn't respect our coefficients. And in this case, if there is the ultimate failure, 2 epoxy resin systems suddenly failed, and everything was hanging on this 1 carbon fibers on very flexible polyurethane. So this deflection that we can observe is still under service limit state, because service limit state was 12.5 millimeters. So if we compare slip, I mean the measured movement of the end of the composite materials. In this case, we can see that blue one and green one line represent both epoxy resin systems, where, as you can see, up to failure, there is practically no slip in the system. In the case of flexible bonding, you clearly see that just from the beginning, we observe increase, almost linear increase of slippage of the end of this kind of system. And if there is a sudden detachment of these 2 epoxy resin, practically we cannot observe sudden drop of slippage in the behavior, but the slippage, as you can see, is only 2 millimeters. What is very important in this case, if we have such system where we are able to hang the structure, we introduce in the structure some kind of post-failure safety. So this safety is measured by energy under this curve. So if the structure is failed, if we have flexible bonding system, in this case, we add the safety to the structure in the post-failure behavior, so we allow people to escape from the structure. It was also confirmed in another kind of test in Portugal. We had the slab, but we applied not externally bonded system, but it was near surface mounted system, so carbon fiber was installed in groove at the bottom of the slab with 2 kind adhesive, epoxy adhesive. You can see 11,000 of megapascal stiffness. Another one was 7,000 of megapascal stiffness, but the polyurethane flexible bonding was only 8 megapascal system. So we tested 2 kinds of structures. One was uncracked and another was pre-cracked when we installed the NSM system. And this blue and red curve in both cases represent the adhesive with stiff epoxy resin, and this red one, this green one, represent polyurethane. So as you can see, practically this system do not differ so much, but in the case of polyurethane adhesive, we have the post-failure resistance that can improve additional safety to the structure. This is also confirmed when we observe the strain measure on the composite material. So if we have such ability that we can apply this kind of flexible bonding, it is also useful to integrate it with some kind of fiber optic measurement system that can monitor the structure after failure. So in this case, we give authorities post-failure information how the structure works, if it is safe, if we can still use it, and what can we do with it. Also, I would like to show you some example of tests with not damaged concrete, reinforced concrete beam. So in this case, with the same system, we used the same type of carbon fiber, but only difference was with epoxy resin in one case, and 4 polyurethane adhesives layer on the other side. So you can compare the Young modulus of this system. So epoxy resin had 12,000 of megapascal, polyurethane PT 600, PS 8, PST 6, and 2.5 megapascal. On the other hand, you can compare the elongation. We start from 0.22% for epoxy resin up to 150 for PSM type polyurethane flexible adhesive. If we compare in the same scale, on the same graph, the curvature of behavior of this system, and we compare it with reinforced concrete reference system, you clearly see that all this system practically behaves in similar manner. This dark blue line represents the epoxy resin. As you can see the slippage at the end of the system, you can see that practically there is no slip for epoxy resin, but even small amount of slippage, 0.3 millimeters at the end of the system for this PS flexible bonding makes very big difference and improve the behavior of the structure, even with higher capacity that it is in the case of epoxy resin. What is also tricky, when we compare one level of the load, you can clearly see that we received even lower deflection on using flexible adhesive than we use very high strength and stiff epoxy resin adhesive. Why it is? Because, as I said previously, when we have the stress concentration, the crack goes through the stiff epoxy resin immediately and attack the composite material, causing stress concentration. If we have higher stress, we have, of course, higher elongation. In the case of flexible material, we stop the crack in the adhesive layer, redistribute the stress more evenly. So in this case, the peak of stress is lower. So also elongation of the composite material is lower. So in this case, the confinement effect is more promising. This is presented here on the graph. So I would like to add some features of the polyurethanes. I'm talking about a group of polyurethanes that we use, and in thermogravimetric measurements, they showed that they have stable properties up to 200 Celsius degree. So in working in elevated temperatures, the polyurethanes manifest very stable behavior. On the opposite side, when we use the epoxy over 40 Celsius degree, it starts to degrade, so it losing its properties. When we compare the Young modulus behavior according to temperature increase, and we have two epoxy resin. If you use, for example, Sika materials, you know Cicadur 30 and Cicadur 330 in comparison to polyurethane PS, and you can see that the logarithmic scale on the vertical axis. You can clearly see that over 40 there is the serious drop of the properties of epoxy resin. In the case of polyurethanes, there is practically stable behavior. If we compare this single up shear test, when we compare with two temperatures, room temperature and elevated temperature, the system where we bond with polyurethanes, the composite material, to three kinds of substrates, I mean concrete, brick, and timber. In this case, you can compare that in the same scale, practically the behavior is the same, so there is no difference in behavior if we apply elevated temperatures. Also, we did many tests according to durability of these polyurethane flexible adhesives. Please do not identify these polyurethanes with polyurethane foam that we use for installation of windows, because it is completely different special material. And as you can see here, we test it for various aging factors after 1000 of hours and also 3000 of hours. And in this case, no significant influences on mechanical properties of these flexible polyurethanes were observed during these aging tests. Also, if we consider the polyurethane according to hydrothermal properties, in this case, we can say that this vapor permeability is high, and is low, and vapor diffusion resistance is very high. So also, if we compare the properties, thermal properties, as the material that avoid thermal bridges in buildings, it can be comparable in properties to wood. So it is also very good material as with promising thermal conductivity coefficients. We test this kind of material in the special project in Europe, Horizon 2020. It is MiZeroE project, measuring envelope products and system contributing to next generation of healthy, nearly zero energy buildings. In this case, we are obligatory to fulfill the requirements of the European regulations, and we are targeted on the innovative materials, because this kind of adhesive is innovative. Even if we have brilliant idea, we have to move to the market. So if we would like to go to the market, we need some kind of certification confirmed by testing. So in the frame of this project, we create the platform when we help the innovative products to move to the market quickly. My university is involved also in this project, and we are able to testing innovative products mechanically with vibroacoustic testing, thermal testing, and also durability testing. So using these pilot lines, the products of Flex and Robust system, I mean these flexible fiber reinforced polyurethanes, were tested with different tests, and also were installed on the living lab, and now this system is observed during living lab using. To summarize my presentation, I would like to point out two groups of futures. Mainly, I would like to point that strengthening of weak reinforced concrete and masonry structures can protecting the structures against collapse effectively. We using this flexible composite system, we introduce additional post-fire safety and stress redistribution because we use the larger area of bonding material. Also, we have the post-filer deflection that is visible, and it warns the user of the structure, but having a large deflection, also we are able to carry high loads. Filer structure, reinforced concrete structure, when it is strengthened with carbon fibers, polyurethanes, is hanged on this composite material, and it is protected against sudden brittle failure. So this is very promising because give time for evacuation of people, and also give authorities time to decide what to do with this kind of structure, if it should be supported, or maybe can be repaired or strengthened in another way. Also, if we use some kind of carbon fiber strengthening, this kind of solution with flexible bonding is complementary to classically used epoxy resin as it was presented, so it can be used simultaneously to increase the post-filer safety. And also, if we compare fibers bonded with flexible adhesive and stiff adhesive, we can say that we obtained a lower deflection having the same load when we used flexible bonding. And also, when we use the near surface mounted systems, in this case, flexible bonding is as effective as epoxy resin adhesives. FRPU systems also can be used as the emergency protection or quick repair, because it cures very fast in 10 hours when we did repair on shaking table and test the system. So also, this kind of polyurethanes reduce the stress concentration, so protect the composite material. And it is very unique because you cannot obtain such effect using stiff epoxy resin or stiff mineral adhesives. And reduction and the redistribution of shear stress along the whole length help in protection of weak concrete structures when the substrate is weak, and because in this case we do not generate the high stress peak that is responsible for damage of weak substrate. Additionally, I would like to point that this kind of flexible polyurethane is resistant to high temperature, I mean up to 200 Celsius degree, so it can work in elevated temperatures instead of epoxy resin that start to degrade over 40 Celsius degree. And also during aging tests, we did not found significant influences on mechanical properties of flexible polyurethanes. So thank you very much. I am happy to answer questions.
Thank you so much. Thank you so much, Dr. Arkadiusz question. We have one question, but where can I learn more about FRPU? Is one of the question.
Could you repeat? Excuse me.
So one of the audience wants to learn more about FRPU. So he is asking where he can learn about it.
I published this information. If you type my name in the internet with some papers according to composite strengthening or polyurethane flexible bonds, you can find it. And also you can find it some movies on the website of my company, Flex and Robust Systems. You will have this presentation. So just at the beginning of this presentation, in the second slide, there is the name of the company, so you can easily find it. Or you can contact me also I'm a university professor, so my email is also available.
Okay, great. Again, Professor Arkadiusz, question. Thank you so much for joining. I know it's a very odd time, and thank you for accommodating this.
Thank you.